Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the basics of surface energy. Now, surface energy actually is the work done in making a surface film slowly. It is very important to note that obviously surface tension does not allow any liquid film to increase its area, and it opposes any increase in area of the free surface of liquid. So if we are increasing the area of the free surface of the liquid against the surface tension force, then we have to perform some work done, and the work done performed by us is being stored in the liquid film in the form of surface energy. So this is a important concept. Now obviously let us demonstrate this situation. Now let us imagine that there is a U-shaped wire frame. This is a U-shaped wire frame, and there is a movable wire. This wire is movable, and this wire is at this point initially, and we have immersed this complete system into a soap solution. Then we are slowly pulling this movable wire apart so that a rectangular shaped liquid film is started to form. So the word slowly means that the force which we are applying on the wire, F external, is exactly equal to F cohesive. In fact, exactly equals means that it is very slightly greater than the cohesive force, but obviously numerically that difference is not significant, so we are considering that they are just equal. But in fact, to move this wire with the F external is very slightly greater than the F cohesive. So we can take the cohesive force as surface tension into the length of the wire, L. So we can also say that F external is surface tension into L. Now let us suppose that this wire has been moved by a distance of dx in the forward direction. So the area which is the increase in area of the film will be L dx. Okay, and the work done by us, dw, will be equal to F external into dx. Now the value of F external is equal to surface tension into length into dx, and you can see that L dx is obviously the change in area. So dw is surface tension into dA. dA is the change in area. Okay, and this work done by us is utilized as change in surface energy of the film, and this is surface tension into change in area. So finally we can make a formula that delta of surface energy is equal to surface tension into delta of area of the film, or area of free surface. This is a general formula of surface energy. Now let us consider two examples. The first one of them is the example in which we are blowing a soap bubble out of a ring which is dipped into a soap solution. Most of us has done this in our childhood days, and we also prefer it doing in this age also. So in this case we always blow some air into it, and we create this circular film as a soap bubble. So we have to find out the work done in this blowing. So we can say that obviously the work done will be the change in surface energy, and the change in surface energy will be surface energy final minus surface energy initial. So the final surface energy will be 2T. Now first of all, we know that there is air inside the bubble as well as air outside the bubble, So there are two free surfaces and therefore the tension is 2T, and the final surface area of this bubble will be 4 pi r square if we are considering that we have created a bubble whose radius is also r. We are just assuming, so it depends on the question only. So the final surface energy will be 2T into 4 pi r square minus the initial surface energy will be pi r square into surface tension is 2T. So you can see that the work done will be 8T pi r square minus 2T pi r square. So work done will be 6T pi r square. This will be the work done if we blow a bubble out of a ring, and it is assumed in this question that the radius of circular film on the ring and the radius of the soap bubble is equal. Now let us take one more example, which is a very common question in NEET exam and sometimes in JEE mains exam, in which there is a bigger bubble whose radius is capital R. This is a bubble and therefore inside and outside is both air, and we blow this bubble into n smaller bubbles, and we have to find out the work done in blowing these n bubbles out of this single bubble. So first of all, we do not know the radius of the smaller bubble, and to find out the radius of the smaller bubble we have to equate the volume. So the volume of the bigger bubble is 4 by 3 pi r cube, and that would be equal to the total volume of all the smaller bubbles, which is n into 4 by 3 pi small r cube. So if we cancel 4 by 3 pi, 4 by 3 pi, then we can say that the value of small r will be equal to capital R upon n to the power 1 by 3. Okay, and now the work done will be equal to the change in surface energy, and we can also say that it would be the final surface energy minus initial surface energy. Okay, now the final surface energy will be the surface energy of all these n bubbles. So for n bubbles we multiply with n, and the surface energy of one smaller bubble will be 2T into area of the smaller bubble, which is 4 pi r square, minus the initial surface energy will be the surface energy of the bigger single bubble, which would be 2T into 4 pi capital R square. Now we can say that the work done will be 8 pi T small r square, which is capital R upon n to the power 1 by 3. So it would be r square upon n to the power 2 by 3 and into n minus 8 pi T r square. So work done will be equal to 8 pi T, and the r square is common, so it would be n to the power 1 by 3 minus 1, and obviously this work done will be positive because n is more than 1, and therefore n to the power 1 by 3 will be more than 1. So this work done will be positive. So this was the two examples and the basics of surface energy, and in the next video we'll be using the concepts of surface energy to find out the solutions of some complex problems. Thank you.